session. We've heard a lot about all of the amazing science we can do with benchmark systems. And next up, we have Gemma Cheng, who's going to be telling us about finding new T-dwarf companions.
Hi, I'm Gemma Cheng. I'm a second-year PhD student at the University of Hertfordshire, and with this wonderful group of people here, I have been working on finding some T-dwarf companions to Gaia primary stars. So a quick outline of what I'm going to be talking about today, a quick introduction, not that I think that it really needs it, now we're at the end of the Splinter, but then I will outline our initial candidate selection, give a quick overview of how we constrained our initial candidates, summarize our observations that we've got so far, and run through our sample of T-dwarf companions. So, as we've heard in all the talks this afternoon, lone brown dwarfs are notoriously difficult to characterize because of the degeneracy between their age, mass, and temperatures. But binaries mean that we can infer the brown dwarf properties from the primary star by assuming coevolution. If we know the properties of the brown dwarf, we can use it as a benchmark. And one of the key things that we've been looking at in this work are the types of primaries, because the different types of primary can give us different information about the T-dwarf companion. For example, white dwarfs, which I'll get to later. So we've been looking for new mid to late T-dwarf companions around Gaia detected stars using VHS 6th data release and DES second data release. The search is sensitive to roughly T5 type objects out to around 100 parsecs. And because Gaia has such good data and the Gaia stars are so well characterized, we can infer a lot of properties from the Gaia primaries for the brown dwarfs. I assume that most people here have seen this discovery photo of the first confirmed T-dwarf. It was only 30 years ago that we found the first T-dwarf, but in those 30 years, we still don't very well understand T-dwarf physics. So we need more benchmarks to understand the physics of the clouds and the chemistry that happens inside these objects. VHS and DS have been used before to look for T-dwarfs. I won't list off everything that's different, sorry, but here's a quick summary of some of the key differences between our work and previous studies. But in essence, our search aims to look for T-dwarfs deeper than ever before and to push the limits of proper motion measurement accuracies. So our list of potential primary stars came from Gaia DR3. We set a parallax limit of less than 5 milliarc seconds to make sure that our upper distance limit wouldn't be too far away, where a mid-T type object on average will be at the VHS detection limit. We also required the proper motion to be greater than 50 milliarc seconds per year so that we could measure it over a baseline of around 5 years. The T-dwarf candidates were taken from VHS DR6 and DES DR2. We cross-matched them together and required a 7 sigma J-band detection and a 5 sigma Z-band detection. We didn't require detections in other bands to keep candidates in the sample, but we used a bunch of color cuts, which are in this table here, to reject any candidates which are likely not to be T-dwarfs. And then we matched our lists of Gaia primaries and T-dwarf candidates out to 1 degree and discarded any of the pairs that had projected separations greater than 20,000 AU because they're not likely to be true wide binaries. We got rough approximations of the directions of the proper motions of the T-dwarf candidates by cross-matching the Vista coordinates with Catwise 2020 and also converting the VHS coordinates to the Catwise epoch. And we discarded any T-dwarf candidates that had proper motions in directions that were different to the Gaia star proper motions. Any Catwise non-detections were retained in our sample, but we did a couple more color cuts to refine our sample further. And then we did a angular separation and positional alignment requirements to make sure that the two objects would be far enough apart to be able to actually see in our images and to make sure that our proper motion measurements would be accurate. So all of this gave us 445 initial pairs of T-dwarf candidates with their Gaia stars. They have spectral types ranging from T1 to T9 and a range of absolute J-band magnitudes that reach up to the VHS detection limit, and their separations range from 376 AU to nearly 20,000 AU. So we've got a big range of separations. We use J-band and H-band VHS observations and Z-band and Z-stack observations from DES. We combined them in a bunch of different ways and compared the candidates' proper motion with the Gaia stars' proper motion. And we categorized it into one of these 4 categories. Good meant there was common proper motion between the T-dwarf candidate and the Gaia star. Maybe where the candidate's proper motion spans across both 0 and the Gaia stars proper motion. Need more epochs where the VHS epoch was within the Z-stack baseline, and reject where there was just no common proper motion whatsoever between the 2 objects. We observed some of our candidates with the Magellan Bard telescope in Chile. We prioritized our observations with likelihood functions, which we calculated for each candidate pair. We used the 4-star instrument to get J-band near-infrared images, and the FIRE instrument to get a spectra of some of our best candidates. But technical difficulties have meant that I've not been able to actually reduce those spectra yet. So unfortunately, I've not got any pretty spectra to show you. Here we can see some common proper motion. This is a white dwarf and T-dwarf candidate. We got J-band images of 48 of our candidates and spectroscopy of 6 of our best candidate pairs of the T-dwarf candidate in the pairs. Hopefully, I'll be able to get those spectra reduced, and we'll be able to do some proper classification to verify that they are indeed T-dwarfs. We measured false positive probabilities for each candidate. It's basically just the number of T-dwarf line of sight associations that we would expect to find within the parameter space of the candidate. And using this, we got 10 good confirmed companions where we are certain that they are true companions. This is the equation that we use to calculate the false positive probability. It's basically just Bayesian inference. where H is the hypothesis that the candidate is a false positive and E is the parameter space of the candidate. To measure the proper motions, we use the oldest available VHS epoch and our new 4-star observations. We did astrometric calibrations in Starlink Gaia, which gave us errors for the calibration process, and we centroided the T-dwarf candidates using the Starlink Gaia pick object tool, and then got errors using the IDL code. This plot here shows our proper motions of our 10 good candidate pairs. The blue objects are the primaries, the red objects are the T-dwarf candidates. They have 1 sigma error bars. So some of our T-dwarfs have T-dwarf candidates have quite big errors, which is mostly down to the quality of our observations. But all of the proper motions lie within 2 sigma of each other, and we have got some particularly nice, really big proper motions, which are quite interesting. Photometric spectral types were found using the method outlined in Schurpek et al. 2015. We made a template of T0 to T9 across a bunch of different photometry, and did a reduced chi-squared to fit the template to fit each candidate to the template. Errors we got by fitting a 6th order polynomial to the chi-squared values, working out where a 1 sigma standard deviation is, and then calculating the difference between the 1 sigma error spectral type and the best fitting spectral type. And here's the photometric spectral types of our 10 good objects. Our final sample has our 10 common proper motion pairs. We've got some GIFs of 2 of them. 6 of the pairs, we have a spectrum of the T-dwarf candidate. 5 of them have white dwarf primaries. I'm not sure what's happened with the formatting on this slide, but white dwarf primaries are particularly nice because they give us some nice age constraints for the T-dwarf companion. As of this French et al. 2023 paper, there was only 7 T-dwarf, white dwarf binaries. So our new sample of 5 nearly doubles that sample. And I've run out of time, so I'll leave you with my summary.
Okay, we have time for a couple of questions.
I wonder, the stars.
We've looked at the Banyan Sigma moving group probabilities for the primaries, and none of them are young. No, we've got the 5 white dwarfs, and then the other ones are all mostly sort of early M type stars, but none of them are young that we've been able to find so far.
Thank our speaker. Well, everybody, that was our last talk of this session. We don't have too much longer left, but in our last couple of minutes, we just kind of wanted to open it up to like a group